Okay. Time to work on electronics, boys. This is good. This is really good. It's been a long time. Too long. It's been too long. Robotics time. That's what this is. Ooh la la. It's been a while since I looked at this thing. I just went through it all. I was able to trace everything. This is just a review, but I'll just go over it real quick. So this is my, what's it called? This is my 7805 5-volt regulator. This is the capacitor on the high side of it. This is the capacitor on the low side of it, going from center pin to right pin. The right pin is 5-volt output, center pin's ground. The left pin is 6.2 to 35-volt input, and the right pin is, again, or the right connection is the center pin, which is ground. So that covers these two capacitors, which just go with the 7805 regulator. The rightmost one is ceramic, leftmost one is electrolytic, and that's what I saw recommended, but you could use electrolytic on both, I guess. Ceramic is good to get rid of small ripples. Okay, and then here we have our capacitor as close as possible to pins 7 and 8. Pin 7 is VCC, pin 8 is ground. It's supposed to get rid of any ripples that could cause corruption. And also provide for mini power surge needs of the microcontroller. Okay, so coming out the right pin of this, we've got a wire heading into pin 7, coming right through here, and forking off that pin, which is our 5-volt line, we have a fork that goes to our LED, which will be an LED indicator when it's getting power. And then coming off the ground side of the LED, we have a 220 ohm resistor, which goes to the ground, and I connected it to the ground up here, because I have a ground line and a power line running around the whole perimeter, which come out here. They're colored appropriately, red for power and black for ground. And then I also have a on-off switch, or actually a reset switch. It's connected to ground here on the same line that connects the ground of the LED, and then it connects to power here. So when it's pressed, it shorts ground to the reset pin and resets the microcontroller, starting it from the beginning of its program. So that covers everything that's on here. That's a total of 1, 2, 3, 4, 5, 6, 7, 8 components, plus the microcontroller and microcontroller socket that it's snapped into. So you can pop it out and put it into a different board to program it, and then pop it back in. I still need to add the quartz crystal oscillator, 16 megahertz, as well as the 2 ceramic capacitors that go with that. and those will be connecting to pins 9 and 10, which are, let's see, the bottom left is 14, so 13, 12, 11, 10, and 9. So these are going to be right below the VCC and ground. So this pin and this pin are going to fork out to the crystal oscillator. So we're going to locate the oscillator and the two ceramic capacitors that go with that right around here somewhere in the available area. I could have sworn I've already soldered. Oh yeah, I did solder capacitor to my other circuits. I made two other circuits for this Arduino. One's a charging circuit and one's a programming circuit. Okay, so yeah, this is our actual circuit that's going to go into our final product, which is going to be our power supply. So right now I gotta look for that oscillator. It's in this baggie. I put everything in the baggie that I will need for building what I'm trying to build. Looks like I put stuff I don't need to. I don't know what. There's a lot going on in here. But we'll figure it out. Maybe I should just dump this out onto this board. It'll be easier to find everything in it. Hopefully nothing gets lost. Because it took a while to gather all these parts. There's a lot of parts to deal with. Okay, here's our quartz crystal oscillator here. And 18 picofarad and 22 picofarad ceramic capacitors we need. 104. Uh-oh. What's this one? This one says 22. That's probably the one we want. This one also says 22. 104 again. Huh. If it says 104, I think that's a microfarad. Let's see. Okay, both of these are 104s. Yeah, I think that means 1 microfarad. Oh, it's 0.1 microfarads. Okay. Okay. So both of these capacitors come together and then they go to ground. Oof. They go to ground. Interesting. That's the center pin. Okay, that's not too bad. I can do that. Oh, I could even connect to right here. Okay. That won't be a problem. I want to see how I did it before on my other stuff. It's good to learn from your own previous experience, and I just have to refresh my memory on how I did it. I'll pull out my other completed circuits that I did with this stuff in the past. Alright, what do we have here? Well, it looks Looks like I can see right here. Okay, that's that one. Wow. Very interesting. Yeah, I'm not doing it like that. I had my circuits huge and spread out before. I'm doing tighter stuff on this board than I ever did on past stuff, so it'll be different. Trying to condense things. This is very small. There's a lot going on in a small area. So, tricky, tricky, tricky. Oh. Wife has my electronic side cutter stack, nabbit. Bad wife. She uses stuff and doesn't give it back for ages. The robot's not done yet. Can't you see I'm working on it? What more can you ask than good progress? I'm putting in an effort, coach. Alright, how in the heck do I need helping hands for sure. This is gonna be quite crazy. Okay. You can do that, I guess. I don't even know if that's the right approach. How do I want to do this? Okay. Yeah, that'll work. Oh, you guys can't even see. My bad. I got the part held in by the helping hand. Oh, snaps. I need all my stuff now. My fume extractor. And get out this thing. And this thing. And this thing. Got to move slowly, man. This is tedious work. Very tedious. The most tedious possible thing you could do in this life. Oh my gosh. Small scale electronics. No joke, man. Oh, it's beautiful. Nailed it. Nailed nailed it. Larry just nailed it. Let's see some applause in chat. Thank you. Thank you. Here every week. I'm here every week. Okay. Beautiful. Got the flux. Now for the solder. I didn't like that. I feel like I didn't get a good joint going. Let's try it again. Oh my gosh. I touched the side of the socket. I got melting plastic on my tip. Okay, how are we now? What in the heck? Okay, that time it just popped off. I'm having the hardest time here. Normally, I one-shot these joints. I don't know what's going on this time. I'm gonna try to scratch off the leg of this socket. Don't know why. Stick to your socket. Wait a minute. It's supposed to go... No, that's fine. Yeah, that's fine. We can do what we're doing. Yeah, I don't know, man. Oh, I know what to do. I'm gonna pre-tin? That way you can't go wrong. Unless you have way too much solder, I guess. Oy vey. Pretending everything, man. Time to stop playing games with this punk. Gosh. I failed again, sorry guys. I don't know what it is about this joint. It's just the most crazy thing. It's like the pin of this socket just doesn't want to take solder or something, I don't know. Actually, it might be on there. Let me check it with magnification. I try not to rely on magnification, but I think that's kind of the point, is to use it in particular to check joints. Just to check them at least. I mean, normally I can check them okay without it, but this joint seems like extra small and hard to see, I don't know. I think I got it, guys. I think I made a good joint. I'm just cleaning up burnt stuff. Alright. I just glued on the black wire that goes around the perimeter a little better. It was kind of loose. Came undone a little bit. Just tack glue it in place with hot glue. The point of these two wires that run along the top perimeter is just to bring the 5 volts and ground around to this side of the microcontroller, where we can connect it for the analog input related stuff. And I wanted to do it in a way where it's out of the way of all the crazy stuff going on in this little section. So anyways, that's one part down of 3 we got to put in this little region. Next we need the oscillator, or we could do the other capacitor. I don't know. I don't know which one I should do. Well, I should definitely do the capacitor first. Hey. Oh, here it is. This is just getting crazy. Overcrowding central. Freaking mess of components going on here. What a mess. goodness, man. Alright, I got that thing positioned perfectly. I think positioning thing is really the key to all this. You just gotta get everything lined up and held down while you get ready. Oh, soldering station's off. I shut it off frequently. Show you guys where I have it while we wait. Alright, so it's this capacitor here. It's this one. So I just soldered this one onto this pin, and I also soldered it to the center pin of this 7805 regulator, and it got soldered on right where? Right here. You can't really see, it's just such a mess. I'm gonna make another solder joint right here. Right here. I don't know. The point is, you can't really see that well, but this one and this one are my 22 picofarad capacitors that will go with my quartz crystal resonator, which will go somewhere around here. I'll stick it. But I want to keep it away from these pins because we want to be able to use these, so I'll put the component like probably over here more. Like kind of behind this electrolytic capacitor. Are you saying that I'm Doc on Back to the Future? I've never received such a great compliment in my life. Alright, I'd crushed that one. Perfect joint. We nailed it. Nailed it. Alright. See if we can nail this joint. Ah! Crud! That would be a fail. Man. I'm gonna need a precision cut. I'll have to use my toenail clipper. I'll keep that in mind. Terrorist attacks are not good for time travelers. Okay. Yes! I made the precision cut I needed. We're back in business, boys. Alright, I'm pretending this. I need any advantage I can get, man. I'm a poop creek without a paddle right now. This is just a nightmare, man. I don't know what it is. Okay, pretending first. Okay, that went well. Now let me pretend the socket pin. It's not taking it. Maybe it is. The socket pin does not like solder that much, I can tell you that. It's like, I could take it or leave it. Not cool, man. That was a big success. You know what? I think the difference is I'm working under magnification now. I think it's helping me a lot. I think I need to keep the visor lens on. This stuff is just too small to work without it. We're getting into some tiny clearances. Let me look at this. Anyways, I'll show you my work I did. If this camera can even hack it. Okay. We just soldered that pin in. We solder that one and that one. And this topmost one goes to that capacitor. And this bottommost one here goes to that capacitor. And then these both fork and they connect to the right leg of this capacitor. And I'm trying to show that connection. It's somewhere deep in here. Somewhere in that little ball. They all come together. I'm trying to show it from different angles. Maybe you'll be able to see what's going on. You can inspect the pins of the socket here. I don't know, it's tough to see the rightmost connection of the two capacitors I just put in. But yeah, there's a lot going on in this area at this point. It's kind of insane. But I can assure you, everything is connected. I can see it better because I have like my magnifier thingy. Okay. And now we have to place this quartz crystal oscillator somewhere. I want a nano lens now. Thanks for that idea. Okay, so this oscillator needs to connect to the rightmost leg of the two capacitors we just put in. Lol. That is insane. No, I think I'm gonna have to go low with this one. I'll lay it on its side. Laying it on its side, guys. You got to lay down, my friend. I mean, the aim is to let everything always be accessible to desolder, to inspect. So I can't have parts overlapping each other visually. I need to be able to visually trace everything with my eyes. I need to be working under the visor at all times. I keep going to regular vision mode, but without the magnification, it's just like kind of ridiculous at this point to see what the heck's going on. Wow. That went very smooth. Good. Okay, we just got one leg of it in. Hey, if I'm so dumb, then how come I'm building the world's greatest robot? I don't understand. This is absolutely ridiculous looking. I got the oscillator mounted up underneath. Here it is. Mounted underneath the electrolytic capacitor that's at a 45. The reason that's at a 45 is so I can see where it connects to the center pin of the 7805 regulator, which is the big black box here. So yeah, the quartz crystal oscillator is right here, and it's chilling underneath. But I don't need to be able to see that so well, so it's okay to be under something. I just need to be able to see the joints, and you can see I soldered it right here. Right there. I soldered it to the right leg of the rightmost one. The rightmost capacitor right there. So now I've got to solder it onto this leg right here. You can see I got it all lined up, ready to go. And it's going to end up in that pin. So everything's lined up nicely. That'll be an easy joint to solder because it's already just kind of hanging out in place. All I got to do is add my flux and then drop the solder on. And we'll be all good. Oh yeah, that was a nice, clean, fast joint right there. Bam. I'll show you guys it. And it's right here. It's the one closest to us. Pin joins to the rightmost pin of this capacitor and to the rightmost leg of this quartz crystal oscillator. They all fork in and connect to the pin coming out of the socket that the microcontroller is plugged into. So yeah, we did it. And I'll show you guys what part of the diagram we just completed. So here's our microcontroller, and here's the oscillator, and the upper pin of it goes to this 18 picofarad to 22 picofarad ceramic capacitor. It could be 18 or 19 or 20 or 21 or 22. We chose a 22, and then it goes up and over and into the crystal pin, which is pin 9 of the AT-Mega 328P microcontroller. Pin 10, the other crystal pin, comes out. It goes to our other ceramic capacitor, and then it forks out and goes to the bottom or right pin of the quartz crystal oscillator, 16 megahertz. And so we just put in these 3 parts, and then the 2 pins coming off this other side of these 2 capacitors forks into our ground line, which in this case we connected it right to the center pin of our regulator, which is part of the ground. And you can see the wall wart's going to come in, capacitor before and after the regulator. Here's the 7805 5-volt regulator. It can take 6.2 to 35 volts and drop it down to a steady 5 volts, but it needs these 2 capacitors to run effectively. Here we've got our LED and our resistor. This will be our indicator light that we're getting power. We've got a reset switch and our resistor to our reset pin. This reset switch, when pressed, shorts the reset pin to ground, which resets the program running on the microcontroller. We have put in this ceramic capacitor, which has to be as near to the VCC and ground pins as possible. We have it really hugging in tight. I could only draw it right here, though I couldn't draw it any closer, because then that would interfere with the writing on all these pins, labeling them. And so we put in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We put in all 11 parts. Now we got to work on all the parts here on the right side of the microcontroller. So we still got to put in that. And if I can get all those parts in, I'll be able to light this LED up, which is on digital pin 9 PWM. With code, we'll be able to turn this on and off. This LED will light up just when it's plugged in. This one we can play with just to test actually a blink program. So we'll create a blink program. And then we'll just have to put in these 4. This is just a 10 microhenry inductor coil, and it looks like that. I actually put a picture of the part. That's how you draw it in symbols, is like a series of butt cheeks. I mean, they look like little cleavage or butt cheeks. Or you could just think of it as like a spring or like a squiggly line. A rounded squiggle. And then it looks like 2 butt cheeks though to me. Or you could look at it as like 2 McDonald's signs. And then I drew, like, sometimes I use the actual symbol used in circuitry drawings. Sometimes I draw it here, like a resistor is just up down sharp lines, and then a inductor's like curvy lines. So sometimes I put the actual symbol here, but I draw the part on my stuff. I like to draw the part because I can recognize that as a ceramic capacitor. But the capacitor drawing would have been like a rectangle. Normally I'll put that right here just to start learning all the symbols, but I didn't put it for the capacitors. Oh, no. No, that's the symbol for a capacitor right here. It's 2 uppercase T's facing each other at the tops. That's the capacitor symbol. The rectangle is for resistors. That's the alternate resistor symbol besides the up and down sharp-edged line. So there's 2 different ways to symbolize a resistor. But yeah, I didn't always put the capacitor symbol below the part every time. My bad. But yeah, I'm trying to learn what the parts look like and then what the symbols look like as well. So like this visual thing is not just a diagram, it's also notes for me. Kind of noting the name of parts, and then it will say like the actual value of the part. It'll have a drawing of the part, and then in many cases it will also have the symbol that the part would use in a scientific diagram. This is not a scientific diagram, Well, it is, but it's not done in a traditional way. And then I also put notes on like other parts you could use here and what this part does and why it's there. I put a lot of notes in my drawings, and you don't see that also in scientific like traditional diagrams. You don't see cool drawings and like everything's just symbols with them, and they don't have any swirly lines. All their lines are just right angles and straight lines. So I think I draw mine in kind of a more cute, fun way, and it's more playful and flowing and nice and spread out, and everything's labeled, and it's got just a lot of information you can learn about. If you zoom in, you can gain all kinds of stuff. So I think that the way I do it is way better. I wish that the entire industry would switch to the way I do it. And hopefully, once I build my robot army and I'm seen as the leading electronics expert of the world, then at last people will start to copy the way I do it, because the way I do it is superior. Hi, Twitch makes you rich. Yes, you can draw this kind of schematic with colored crayons. That would be the preferred way to draw it on paper. I'm definitely a fan of crayon schematics. This is the Photoshop version of crayon drawings. So basically I'm like a preschooler. But the fact that it looks like a preschooler was scribbling with crayons makes it less threatening, more inviting, more like, oh, how cute, this must not be that complicated. But if you saw like a buttload of crazy symbols and stuff going on, you'd like, whoa, that's too much for me, I don't know what I'm looking at. And then you wouldn't be as willing to like learn it, or you feel too intimidated. You feel like you need a degree in electrical engineering to understand what's going on. So I like that approach. I like to draw my diagrams nice and simple and beginner friendly and non-intimidating. I mean, how complicated can it be if it looks like somebody did it in crayons in their preschool class? That's my philosophy. Okay, so we can keep going, man. We finished that. Now, okay, red is going to come over, which we already have. Red comes off the right hand pin of this, and it comes around, and it comes over to the other side of the board. It goes through a 10 microhenry inductor coil, which we've already selected, and it's on our little part pile on our lap. And it will ultimately end up going into pin 20. Pin 20? Yes, pin 20. Which is analog pin VCC. It's going to go into that pin right here. So it's coming through. Our black one is coming off the ground, or the center pin of the regulator comes around to the other side of the board. That's our ground, and it's going to go to pin 21. The analog reference pin. It also forks and goes into the ground pin, pin 22. And on its way to pin 21, it goes through a 100 nanofarad ceramic capacitor, which I believe is labeled on the ceramic capacitor 104. That's what it actually says, the number on the capacitor. gosh. That is not what I'm hoping for. But Adam might be on that level. We'll see. I mean, that thing looked kind of like poor aim of the ketchup, in my opinion. So let's hope Adam can do a little better job, because he's possibly going to be doing my hair transplant. And if he does my hair transplant like that tank did the ketchup transplant, then I'm going to have hair stuck into my eyes, my cheeks, all over the place. I don't think it will make it to my receding hairline region. So let's hope I can one-up that robot at least. Okay. Why did you just type in butt cheeks now? You guys have to admit, that looks like butt cheeks, man. Look at that. It's a pair of butt cheeks. We're looking down at them. They're like cute little cartoon butt cheeks. A pair of them. Or it's looking down at two women from an aerial view. They're both facing upward. And we're looking down at some really epic cleavage here. Take your pick. Either way. Who said science can't be sexy? I have to disagree. That's one sexy electrical symbol, if you ask me. By the way, guys, do I look cool right now with my headgear? I'll shut off the light so you guys can give me your feedback. This is my new look, I think. I think I look like a real roboticist right now. Watch this. Bam! Oh. Everything's gone. I wrecked it. No. No, it's all falling off now. What the heck? I had it perfect. That's what I get for trying to show off for the lads. Just because I look so cool, I'm trying to make myself show off now. It's getting to my head here. Now this thing needs to be tightened. Ooh. That was good. Man, I look cool with this stuff on. If I walked into a club right now, every girl would definitely want to date me. For sure. They would be like, who's that hot, bald science guy with the crazy headgear? I've never been so turned on in my life. I look like a donkey? What donkey has this much expensive equipment attached to his head? Okay. By the way, I think that this fume extractor makes me look even more cool, if that were possible. So, this red one goes to... Oh man. The inductor coil. Where... The inductor coil comes off the 5 volts all the way through here. Why is it there? Inductor coil, let's see. That probably would smooth out the flow as far as like voltage spiking. Smooths the voltage out, I think. I mean, capacitors smooth voltage out, but I think they're more for like providing for lulls in voltage. And inductors like smooth the rate of power more. Or something. Or like make it not so abrupt in the changes. They carry like an electromagnetic field. Whereas ceramic capacitors just hold like potential. Like electrons mounted up that just bust when things die down. That's the way I understand it anyways. So the question then would be, how close does this need to be to analog pin VCC? Why not have it connect directly? And then we'll have it just fork out and connect to the... So we'll stick this thing like right here, but in the drawing it can be further away. That seems good to me. And then even this capacitor, we can just have, since it forks from ground onto analog pin VCC, we can put it like right here. And then have the inductor coil like right here, just swinging out to where this wire comes in. So yeah, these are drawn far away from the microcontroller for visibility of where they all place and where they all connect, and to draw the symbols and stuff, but where they're actually placed will be a lot different. So that's the plan. We're gonna start off putting in this capacitor real close to ground and analog pin VCC. We'll have it straddling those. Yeah. That's the plan. So that's this bad boy. And that ground pin is, let's see, 1, 2, 3, 4, 5, 6, 7 from the top. One, two, three, 4, 5, 6 pins, and then comes the ground pin. Okay. 1, 2, 3, 4, 5, 6 pins, and then comes the ground pin. So it's going to be the first pin below the white line. Got it. Got it. And we'll want it nice and short. Oh, interesting. The way they do it, or the way I did it before, is I bent it away, and then it just comes out and you can attach to it. That's pretty cool. I can do that again. I'm going to bend it away from the socket. Like that. Need my light back. You would not be surprised. Wait, the only thing you would not be surprised about would be if I was wearing flippers. I am wearing flippers. You're saying that everything besides that you're surprised about. Oh, so you're saying I'm being very surprising right now. Well, that's a good thing. I like to surprise my audience. You guys don't think I got electronic skills? Well, you're about to be very surprised when you find out that's a lie. My electronic skills are second to no one. I'm going to need the helping hands to hold this capacitor in place for me. Yeah. You need to hold on to him, little helping hand man. Get it together here. We have to show our guests how skilled we are together. The helping hand and I are very close. Sometimes we cuddle together in bed, but I can't talk about that on Twitch. It's a little bit personal. If you talk sweet to your helping hand, then your helping hand will help you with even more love and compassion than normal. Helping hand is like man's best friend. Who wants a dog when they could have a helping hand? Oh, snaps. There we go. Just need a better angle. I'm struggling here. You dirty. I told you to hold on. What's the matter with you? Thought we were friends. Replace you with my firstborn child if you don't start holding on to parts when I tell you to. Ooh, Adam can be a great helping hand. If this helping hand doesn't start cooperating a little better, I'll replace him with Adam. What the heck? Okay, that's not even working. Oh my gosh! Oh, the fan just hit my hand. That scared the heck out of me. Alright. What's another way? Just the way the helping hand was holding it wasn't working out. Oh, you know what? I'm gonna use this, I think. Oi! I got an idea. My goodness! The hardest part is just getting the part, like, to sit where you want it so you can solder it. Figuring out how to hold it down. Alright, I think we're good with that. You know what? I'm gonna need to pre-tin everything. Okay. Nailed it! Beautiful. Okay. What the heck happened? Pulled right off. I think I soldered the pin onto a layer of oxidation. I think I have to scrape each socket pin with the X-Acto knife to score it and like remove any oxidation before I solder to it. I don't know. It just seems that way to me. I'm going to scrape all these ones that I'm going to be working with here right now, because I don't like doing a perfect joint and then having it pop off for no reason shortly thereafter. I'm just using the very tip of the X-Acto knife and just scratching it on each pin, making it real shiny. I think the solder will take to that better. It's really weird. It had like this weird dull color after the stuff popped off. So weird. I'm sure that won't happen again now that I just did what I did. Maybe it even had some super glue? Nah. I don't know about that. Okay. Okay. Beautiful. Wow. I'm getting better, boys. I'm getting better. I gotta show you how beautiful these joints came out. Check this out. Nice and clean, no over soldering. I think I nailed it. Get you some light. There we go. So now that capacitor is attached and it's facing outward, so we can connect to these pins with anything coming out this way. And our next thing we want to put in, so that was this capacitor, which forks from ground, which is the 7th pin from the top. It's pin 22 on the ATmega 328P microcontroller. And then it forks all the way around to analog pin VCC, which is pin 20. And so we just did that. It's straddling those two. And now I want to put in this capacitor. This one just connects to the pin right between ground and analog pin VCC. It's the analog reference pin. And so we'll just solder one leg of that capacitor onto that, and then the other leg will be jutting out. It's 100 nanofarads, same as the one we just did, so it will be labeled part 104. And we already have it selected. So we can just spread its legs out in a very non-sexual way. Awkward. And then I want to snip it a little shorter too. Let's see. It's going to go out to, oh, it goes to ground anyways. That's interesting. This one, its left pin goes to the analog reference. Its right pin goes to ground. So basically, it's straddling between this one and this one. Huh. Yeah, ground is the uppermost of the two. Alright. So I'll just have it Y into that one. Yeah, something like that. Let me get that going. That going. Let me set down this nail cutter. Okay. Perfect. I have flux all over my thumb. Not cool, man. Okay. Gotta cut this pin like so. Well, do I want to cut it? Maybe not. Nah, I don't think I need to. Let's see. Let's see. It connects to ground on its rightmost side. It's coming out here. It's gonna connect to the ground. Ground doesn't connect to anything else, by the way. Ground will fork out and connect to that resistor on the bottom right. Over here. Okay, I know what I'll do. So I'll just swing this leg to the right. And down. Yeah! That's what I'm talking about. Okay. That's perfect. I'll show you guys what I've done here. Okay. So this center pin right here comes out, comes into this leg of this capacitor, and then the right leg of it just merges into this pin, which comes along here, and that's the right leg of this capacitor. So that's coming sorry, let's wait for it to adjust. Oh, come on. Okay. So the right leg of this capacitor is coming out and then curving and coming along the edge of the board to here. And they merge right here. And that's the ground leg. And then the left leg of this capacitor in the back comes just out and just stops right here. So this capacitor's left leg just goes to the middle pin. Its right leg merges with the right leg of this one. And there you have it. So we put in both capacitors now. And they're good. So now we can go on to whatever the next part is. Now that these two are done, I really want to do this inductor next, because these two are really optional anyways. They're just for the Blink program. Let's get the inductor. So let's see. That's just running anywhere and coming to the analog pin VCC, but it's got to be outside of this capacitor, so further away than that capacitor, which is the one that straddled ground in VCC. So it's gonna basically just connect to the right leg of this one, or the bottommost leg, the one coming off analog pin VCC. It's gonna just connect right there, so we'll end up putting it right here off a pin. Let's see, 1, 2, 3, 4, 5, 6th pin, 5 from the bottom, it's the 6th. Okay. 1, 2, 3, 4, 5 from the bottom, it's the 6th, yep. It's going to come right off here and then turn and come up. And that's this one. Huh. Okay. So this is what a 10 microhenry inductor looks like. I bought a whole kit of little inductors in assortment, and they were labeled. This one was labeled 10 microhenries. So that connects to here, huh? And then goes to our... It's gonna kind of come off the board. To our BCC after that. Okay. We'll cut it pretty short here. Very good. And it's gonna come right here. Okay. I like to wipe off my soldering iron every time. Put on fresh solder. I don't know how much of a difference that makes, but it seems like it could make a difference. Old solder is probably more oxidized, probably won't flow as well. Hi, Random Gaming. Where's my needle nose? What's it falling on the ground? There it is. Dirty rat. Okay. There. Looking lovely. And Gotta strip the ground wire. Snaps. Messed that up. There we go. Okay. Got it lined up. Ready to make my joint. Oh gosh. Alright, that's good. And then this one. Got a delicate situation here. Trying to strip the red wire really carefully in just a little section so we can connect it to our inductor here. Just press the reset button on accident. Gotta be careful when holding this board I don't accidentally like tear apart a piece off. Everything I do has to be so gentle. That's a bad part about working with insulated wire. It's hard to expose it sometimes. Especially the stranded jumper cable. Ugh. Okay. Now we can do our joint. Whoa. I think my knife's dull. Could have very easily just cut myself pretty bad. Okay. Alright, I just made a nice joint. I'll show you guys what I did here. So I just connected that joint right there. So basically I took the inductor, its wire comes right through here, and then I just connect it to the red. I split some insulation away from the red, and then I just connected it to the exposed red. There we go. So yeah. Then I just let the red keep going, so that way we can come this way all the way across and connect it for our pin 9, or digital pin 9, which is the bottommost one, which we're going to put our LED on. Oh wait, the LED goes to ground, never mind. Huh! Well, in that case, I guess I could just cut this all off then. Well, unless if we might need it for something later? Would we? It's 5 volts. I don't know. I guess I'll just leave it dangling in place for now. The LED, we have one here, goes to digital pin 9. Okay. And then to ground. I see. Man, I'd prefer an LED that has nice long legs on it. Because this LED doesn't have legs, man. Grr. Do we have more LEDs? I think I ordered LEDs. Yeah, we do have LEDs. Yeah. Might use one with longer legs. Oh, these are baby LEDs. Baby size. Okay. Yeah, this one will do nicely. Well, let me just set it out. I don't need to figure out where I'm putting it at this second. This LED bag away. A little tiny bag of LEDs. Look at all those. I'm prepared, guys. No more wait 2 months to get some part I order because I'm not prepared at. I have tons of stuff now. So the odds of me not having what I need are way lower now than back in the day when I first started electronics. I've been stockpiling everything I can think of for the past couple of years. I've been just buying. Okay, so we want to take the LED and go from digital pin 9 to ground. Uh-huh. Oh. I sure would like it if we had ground come. I've been saving these pins, haven't I? Here's one. I'm thinking using a component leg that I cut off earlier. would be a good way to extend ground toward our part. Or not. Huh. Huh. I'm kind of thinking a radical idea, which is to just use this top joint as my ground at all times and just send jumper wire grounds way out to wherever I want. I like that idea. So let me get jumper wire. That way I can see a nice black line. Black wire. Okay. Yeah, we're taking black wire coming through a 220 ohm resistor. Alright, let me strip the wire. And ooh. Nailed it. Okay. Solder that in here. Okay. Now I can take that and just come around all the way. Let me hot glue it in place as it makes this turn. What the? Okay. And then come through. So go to my 220 ohm resistor. Huh. And to my LED. Where's that LED? Okay, I'm gonna scrape away this leg of the socket. I feel like it might have some glue on it. Okay. Should take now. Oh, I just put way too much flux. Okay. Beautiful. And that needs to go through 220 ohm resistor. Before it hits our ground. Here's the 220 ohm resistor. Okay. Good. Now that resistor connects to my ground. Oh, wow. I don't mind if he connects to this ground. Well, nah, I'll put him in this one. Well, I don't know, this is pretty easy though, too. You can go underneath even. Alright. Oops. Straight up beautiful. It's a beautiful thing, boys. I think we just did our last joint there. That completed our connection of the LED to the resistor. So here we have our LED, which goes to this bottommost pin of our socket. Connects right there. And then the other leg of the LED goes through this resistor. Then this resistor comes underneath everything and connects to ground here, which you can see the final leg of that resistor is here. It connects right here. So this resistor just kind of swings under this inductor and connects right there. And I just left these two 5-volt and ground pins just kind of hanging out so I can connect anything else I want if I need it later, and I probably will at some point. But they're just kind of chilling. I don't think they're causing any harm. So I believe this is the completed circuit. So this is an Arduino, guys. It's got everything. Plus it's got all the power management stuff, 5-volt conversion stuff here. So it's a homemade Arduino. It's got an indicator LED. It's got a LED specifically for running a blink program. Here's the indicator LED. Reset button, 5-volt regulator, 2 capacitors to run the 5-volt regulator off of, capacitor between VCC and ground. It's got the 2 capacitors here that go with the oscillator, the crystal quartz oscillators hanging out, kind of hiding under here. And there's our resistor for this LED, reset pin, resistor that goes to the reset pin, which is right there. This is our reset button. You can press it. We got our 2 wires coming off the back side. The center pin is the ground, and this pin on this side goes to our 5-volt output. The rightmost pin of the 7805 is the 5-volt output. And we have them color coded, so we've got red and black swinging around the top ledge. You can see them coming through. They come all the way around, and then they feed into, here's the ends of them, and they feed into the various components here. We got LED and resistor for running a blink program test. And we've got a capacitor going from ground to analog pin VCC, and another capacitor going from analog reference to ground. And that's this one. Analog reference is between the two, so it kind of goes between this one, which is straddling 2 pins. And here we've got our inductor. It's a 100 nanofarad inductor, which goes to analog reference. No. Yeah, it goes to our analog pin VCC. Yeah, it goes to analog pin VCC, and it connects to the 5-volt supply right here. It's got a nice long leg that connects all the way right here. And yeah, our 5 volts and ground we just kind of let hanging out here for now, because I might need it for something later. And that's everything. So that's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 components on something not much bigger than my thumb. So that was hard to me to fit all that stuff onto such a small space. But we did it, and it's still bigger than, I don't know, something like this, which is even smaller and uses like insanely tiny little surface mount components like a cell phone. It's even smaller. But the key to that is it's using printed circuit board technology, not dead bug wiring. It's It's got everything printed, and it's pick and place machines dropping stuff down. It's just crazy technology to make stuff downscale. But for hand soldering, I still think this is pretty cool. Like, I made it pretty darn small for hand soldering, I think. And especially with no printed circuit board stuff, it's all just dead bug style. So that's fun, and it's nice and small. I think it worked out. And now it's just a matter of testing it. So to test it, we're gonna have to program this using our programming circuit, which we created separately. So we'll pop the microcontroller out, pop it into our programming circuit, we'll program it. We'll connect power from a power supply to this. This will regulate it down to 5 volts. And we'll get this LED flashing. But I'm not going to do that right now. I'll save that for next time. I feel like we got done enough for one session. So I'll put that in the next session. But yeah, man, we finished the Arduino. And that means we'll be able to connect this thing. First of all, one other thing. I'm not going to make a homemade Arduino setup again, I don't think. I'm just going to use an Arduino Nano. But I'm glad I learned how to do this. And if you wanted a job in engineering, if you just use an Arduino, that's not impressive. It's all plug and play then. Like, they want to see that you can work with microcontrollers. And in industry, you use an actual microcontroller. So technically, you could say this is not an Arduino. This is just me creating a custom microcontroller setup. Even though it's got all the same wiring. It's like a basic Arduino, and it uses the same chip as an Arduino. But it's a custom board. And that's what a job... If I wanted to get a job in electrical engineering... for product design or something, if I show them this and then I show them how I integrate this into a power supply I design myself, I could actually get a job. Not that I want one, but this is as good as a degree in electrical engineering or a resume. If this thing all works, like, you can literally get a job by showing projects like this. So it's better to do something like this at least once, rather than just always start off with using a complete Arduino board where you didn't do anything and you just connect all the wires with plug and play with jumper wires. This is like showing actual soldering and low level attention to detail, and it's actually hard, and it requires some understanding and a lot of research of all the different electrical components involved and how to source them, how to connect them all without short-circuiting everything. So yeah, this is impressive to people that would hire you. And I think it's cool to be qualified to get a job in a field that I'm an amateur hobbyist in, to say, like, I can get a job in this. I think that's pretty cool. What is this thing for? Okay, so it's like a computer. It's like a mini computer on a board. And you can program it to do anything. To turn on and off little lights, to turn on and off little switches, etc. And I'm going to program it to turn on and off a little light to test it, make sure it's all working. And then I'm going to program it to, you can actually upload software programs to this. I'm going to program it to turn on and off little switches in my switch mode power supply. So I'm creating my own power supply. Use my own custom little Arduino type board, which is what I just finished today. So this board, when connected to my power supply, will be the brains of the power supply. It will switch on and off the board in order to regulate the voltage and create a regulated output. And I can make the voltage anything I want, for the most part. Anything lower than the input voltage. So I'm making a buck converter switch mode power supply. Just like the kind of power supplies you see in a computer, except it's a custom power supply that I designed myself. And it ultimately is going to power my handheld vacuum. That's what this power supply will be for. The one that this board's going into. But it also serves as a prototype for Adam's power supply, and that's why it's something very important to me. And it's also why I can't just use something off the shelf. Plus, it saves money and teaches so many valuable skills to make your own power supply from scratch like this. And it's a great, like, beginner's intro level electronics projects. Well, actually, it's not even really beginner level. I'd say it's fairly advanced. I'd say total beginner would be just take an Arduino board and start plugging in lights and get them to blink, but I actually created my own board instead. So anyways, that was a big win, and we finished this. So now I can, the next time we come back, we're just going to program this board to do stuff and connect it up to power and actually run tests, actually have it doing stuff, actually have it working for us. And from there, we can, once we ensure it's all functioning properly according to specifications, we can attach it to the rest of our power supply board and start turning on and off the power, or turning on and off the little power MOSFETs and seeing what the voltage it's giving us is. So if we come back to our diagram here, this is the Arduino microcontroller, 18 mega 328p microcontroller. Zoom out. Oop. Crap. Alright, so that's the whole diagram. We put in all these parts. This is the regulator, the two capacitors, the LED, the resistor, the inductor, these two capacitors, the other LED for the blink program, the resistor on that. This is just an indicator LED that is plugged in. The resistor going to the reset button, the reset switch, the two capacitors that go with the crystal quartz oscillator. And so yeah, I put in all this stuff. This is our wiring for a standalone 328p microcontroller. That's basically our Arduino. And then here is it again shown as part of a grander design where it integrates with our buck converter, which is all up here. And here's the main switch for the buck converter and the secondary switch. Here's the inductor coil, and then here's the output capacitor, pair of input capacitors. Here's our diode bridge rectifier. Diode bridge rectifier, pair of capacitors, a fuse, crowbar circuit, main switch, secondary switch, and you can see this is where that whole board is that we just put. This is all one board. That's the diagram. It's spread out here, but all this went on that little tiny board. And this board then is going to be connected to all these little MOSFETs, which are going to control the regulated output, which will come out through here. And it will be regulated by reading the voltage here. This is a voltage divider that will enable this board to read the output voltage. And yeah, that output voltage will eventually go to our vacuum, which will plug in right here. And that will go to the vacuum's motor, which is right here. And it will also go to the vacuum's battery pack, which is right here, all the batteries. And here's a second microcontroller board and a second buck converter, which will lower the voltage again down to what these batteries want to charge them, which is 4.2 volts, I believe. So yeah, we are through now. This part, these two parts, this part, this part, this part, this part's in. All these parts are now done, so now we just got to make a few of these parts all connected. Maybe another like 20-30 parts. Like all this, but like this entire 2/3 of it's already done. We just got to do this little section here. All this is still to go, and all this is done. So once we finish that, then this whole thing will be a buck converter, a switch mode power supply, all this. And it will be capable of 18 volts, 100 amps, which is pretty crazy. That's 1800 watts. So your computer has like a 500 watt power supply or a 600 or 700 watt power supply. Mine's going to have 1800 watts capability. So I'm making a really powerful power supply. It's way overkill for what I need for the vacuum, but it's designed to handle the high power needed for Adam. Adam's going to need as much power as he can get. In fact, Adam's going to need like multiple of these power supplies. He's going to need 2 complete house circuits, normal 120 volt outlets. He's going to need like a couple of those, or maybe even 3 of them to power himself when he wants to use all of his muscles at once. He's going to eat up, let's see, 120 volts times 10, that's 1200 watts is the normal output of a single circuit of a house before you flip the breaker. So 1200 watts times 3, that's 3600 watts. That's the kind of watts Adam will require to do like more strenuous things like lifting up heavy stuff or whatever. So he's going to need a lot of power. Now, he doesn't need it necessarily all from the wall. He'll have batteries, so he can pull all that from all of his high output batteries. But I want to have the option to have Adam run off the wall. If all of his batteries are low on power, I want to be able to plug into a few wall outlets and run directly off the wall, which will save the batteries from, wasting their battery life. He doesn't need to run on batteries if he's just hanging out in a room custom designed for him to be working in night and day. So in that case, I would prefer to have a setup where he can run purely off the wall and let the batteries just chill. Why, run down these expensive batteries, using them over and over day and night, week in, week out, year in, year out, when the batteries can just not be used at all unless if he's switching rooms or something like that. So I want him to be able to run off really powerful power supplies that are designed to be small. Small form factor, lightweight, incredible power. That's why I designed all these power supplies like that. So he's going to run off multiple power supplies plugged into multiple wall outlets. And I'll run 3 circuits from the breaker box in the garage to my room. And each one will have a wall outlet, and he'll plug into all 3 wall outlets, which will be mounted on the wall next to each other. He'll plug into all 3 and get tons of power from the wall. And then he'll have all the strength he needs to do any type of heavy manual labor he might need to do.